Right, listen up. Welcome to another explainer. If you're facing down the Cambridge IGCSE Mathematics syllabus, specifically code 0580, you already know that data handling is absolutely not just about looking at pretty, colorful charts. It's a high-stakes game. It is about precision. It's about spotting the examiner's hidden traps before you fall into them. And most importantly, it's about assembling your ultimate team of cognitive specialists, your tools, to pull off the perfect answer heist when the pressure is on and the clock is ticking. You see, I constantly see two types of students. You've got Alex, who completely overloads his paper with raw mathematics facts, but does zero actual analysis. And then you have Sam, who rushes in panic, completely misses the command word requirements, and throws away easy marks. We are not going to be like Alex, and we are not going to be like Sam. Today, we are building your strategy. We are assembling your ultimate data toolkit so you can walk into that exam room and flawlessly execute.
Okay, here is the master plan for today's heist. Section 1. Discrete versus continuous data. 2. Comparing data sets using stem and leaf diagrams. 3. Proportions in pie charts. 4. Finding correlations in scatter diagrams. And finally, Section 5. The dreaded histogram challenge. This is the exact roadmap you need to master. Let's get to work. All right, Section 1. Discrete versus continuous data. Now, before you even think about drawing a single chart or calculating a single mean, median, or mode, you have to know exactly what kind of data you are actually looking at. This is the foundation. If you get this wrong, your entire strategy collapses. The examiner specifically tests your ability to categorize data because it dictates every single visual tool we use from here on out. Look closely at how clearly these two main data types separate. It's like night and day once you see it. Discrete data has specific, fixed, rigid values. It's counted. Think about opening a packet of chocolate buttons. You can count 35 buttons or maybe 36 buttons if you're lucky, but you literally cannot have 35.4 buttons. It doesn't make sense. The same exact logic applies to a golf score. You simply cannot score a 70.5. It's a hard, fixed number. Continuous data, on the completely opposite hand, flows seamlessly because it is measured, not counted. Time, weight, speed, or the height of a growing sunflower. These can all be measured to an infinite number of decimal places, depending entirely on how accurate your stopwatch or your ruler is. Sam always rushes and treats height as discrete, losing instant marks. Knowing this difference is your first key to unlocking the right visual strategy.
Moving to Section 2. Comparing with stem and leaf. So let's say we have a whole bunch of that discrete data we just talked about. And we need to organize it clearly. But here is the catch. We cannot lose any of our original raw numbers. We need a specific tool for this job.
Enter the back-to-back stem and leaf diagram. This is a brilliant piece of mathematical strategy. It illustrates exactly how to compare two totally distinct sets of data at a single, rapid glance. We're going to do a quick data scan challenge right now. Look at these ages of holidaymakers. On the left, we have passengers on a coach to a ski resort. On the right, a coach to a golf resort. The stem right down the middle represents the tens column, so the 2 means 20s, the 3 means 30s, and so on. The leaves stretching out to the left and right represent the individual units. By placing this data back to back, it becomes instantly visually obvious without doing any heavy math. Look at the golf resort passengers on the right. Their leaves cluster heavily down in the 50s, 60s, and 70s. They are clearly generally older. Now look at the ski coach passengers on the left. Their ages are tightly bunched up top in the 20s and 30s. We literally haven't lost a single raw data point, but we've gained an immediate, powerful understanding of the demographics. By the way, before we continue, subscribe to our YouTube channel Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. You need these strategies in your feed.
Let's move smoothly into Section 3, Proportions in Pie Charts. We're pulling out another highly visual tool to display discrete data. This one is specifically engineered for when we want to see how a whole population is divided into its constituent parts.
Now, the pie chart is incredibly popular because it's just so intuitive to the human eye. For example, look at this survey. We asked 240 English children about their favorite holiday destinations. Instantly, your brain registers that the blue slice representing Spain is the largest. But here is the reality check. In a Cambridge exam, you aren't just looking at pretty colors. You are required to calculate the exact precise size of those slices based on the raw frequency of the data. Alex usually writes down all the raw numbers, but doesn't know how to convert them. Let's fix that.
The absolutely crucial secret to cracking the pie chart is this magic number right here, 360.
A full circle has exactly 360 degrees. To draw a mathematically accurate pie chart, or to do the reverse and work backward from a drawn pie chart to find the original data, you have to remember one golden rule. The total frequency, which in our previous survey was all 240 children combined, must be perfectly proportionally mapped onto those 360 degrees of the circle.
And here is the exact step-by-step mathematical formula you need to commit to memory right now. Step 1, identify your total frequency. Step 2, take the frequency of the specific category you are calculating and divide it by that total. This turns it into a fraction. Step 3, multiply that fraction by 360 degrees. Let's say 80 out of our 240 kids chose Spain. That's 80 over 240, which simplifies beautifully to 1/3. 1/3 of 360 degrees is exactly 120 degrees. So you grab your protractor, you measure exactly 120 degrees, and boom, you've secured your method marks and your accuracy marks. This is how you systematically dismantle a pie chart question.
Let's keep the momentum going. Section 4. Correlations in scatter diagrams. We're shifting gears here. What if your mission is to investigate whether two totally different variables are actually connected to each other? For that specific job, we pull out the scatter diagram.
Scatter diagrams are all about one thing: correlation. And correlation is really just a fancy mathematical word for relationship. Now, Cambridge examiners are actively listening for a very specific vocabulary when you describe what you see. You can't just say it goes up. If the plotted points slope upward from left to right and are tightly packed around a central line of best fit, you must call that a strong positive correlation. If they slope downward and are tightly packed, that's a strong negative correlation. If they form a clear directional trend but the dots are a bit loose and scattered, use the word weak positive or weak negative. And if the graph just looks like a random chaotic cloud of dots floating in space, you state firmly that there is no correlation. Using these exact phrases is how you show the examiner you know the rules of the game.
Now, I need you to pay extremely close attention here, because we are looking at a massive trap that catches thousands of rushing students, like Sam, every single year. The source material highlights a classic example: plotting the heights of children under 5 against their body mass. Unsurprisingly, it shows a nice, strong, positive correlation. As kids get taller, they generally get heavier. But what happens if you take your ruler and blindly extend that line of best fit way, way past the data you actually collected? Say you extended it up to a height of 2.5 meters. You end up mathematically predicting a completely impossible, ridiculous body mass for a gigantic toddler. The golden rule is simple. The line of best fit is only reliable within the range of your actual collected data. Never, ever extrapolate into the unknown. It ruins your analysis. Stop scrolling, subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, take a breath. We are entering Section 5. This is it, the histogram challenge. This is essentially the final boss of the data handling syllabus. It is notorious, it is tricky, but we are going to break it down perfectly.
First things first, we must clear up a massive, fundamental misconception. A histogram is absolutely not just a bar chart where the gaps have been removed. They operate on completely different rules. In a standard bar chart, the height of the bar directly tells you the frequency. Simple. But in a histogram, especially one representing continuous data, the bars are joined, and it is the area of the bar that represents the frequency. Let me repeat that. The area, not the height. Now, if all the bars happen to be the exact same width, then sure, the height conveniently matches the frequency. But let me tell you, Cambridge examiners rarely make it that easy for you. They want to test if you really understand the concept.
So, let's do an interactive workshop right here. I'm putting 60 seconds on the clock. In your head, take a really close look at this specific exam scenario. A gardener has measured the continuous heights of 25 sunflowers. Scan the data table. Look very closely at the intervals. Do you see the trap? The first group goes from 0 to 1.0 meters. That is a massive class width of 1 whole meter. But look further down. The interval from 2.0 to 2.25 has a width of only 0.25 meters. The data intervals are completely, wildly unequal. This is the setup for the perfect heist by the examiner.
So, challenge number 2, find the flaw. I want you to think about this logically. If you were to rush this and plot this data exactly like a standard bar chart, putting the raw frequencies straight onto the vertical y-axis, what would realistically happen visually? What is the fatal flaw in doing that? Here is the absolute truth pulled straight from the examiner's textbook. If you plotted that first group, which has a frequency of 6, over that massive 1-meter width, you would end up drawing a gigantic, visually overwhelming wide box. Visually, the sheer area of that box would completely dominate the graph. It would trick the human eye into thinking that the vast majority of all the sunflowers were under 1 meter tall. But in reality, only 6 out of 25, about a quarter of them, are in that group. This visual deception is exactly what you are being tested on. The examiner wants to see if you will fall for the area trap.
To completely disarm this trap, we need to mathematically flatten the playing field. We have to adjust for the varying widths. And we do this by calculating something called frequency density. This is your absolute secret weapon for the final boss. The formula is beautifully simple. Frequency density equals the raw frequency divided by the class width. Burn this formula into your memory.
Let's see that specific math in action right now. For our first group of sunflowers, the frequency is 6 and the width is 1. 6 divided by 1 gives us a frequency density of 6. Now look at the second group. The raw frequency is only 3, but the class width is a narrow 0.5. 3 divided by 0.5 mathematically gives us a frequency density of 6. Do you see what just happened? By factoring in the width of the group, a lower raw frequency can actually result in the exact same or even higher density. This entirely changes how the data looks.
And this brings us to the final bulletproof solution. Whenever, and I mean whenever, you encounter unequal class widths in a Cambridge exam, you completely abandon plotting raw frequency on the vertical axis. Throw it out. Instead, you plot your newly calculated frequency density. When you do this, the area of each bar, which is calculated as width times height, will flawlessly equal the actual frequency. The wide bars get shorter, the narrow bars get taller, and the visual deception is destroyed. It becomes a mathematically perfect visual representation of the truth, and it is exactly what guarantees you the full 100% of the marks for that question.
So, let's recap our system. We have organized discrete data flawlessly with stems and leaves. We've mapped proportions perfectly to a 360-degree circle. We've respected the strict limits of our scatter diagram correlations to avoid ridiculous predictions. And we have totally conquered the unequal histogram trap by mastering frequency density. The toolkit is yours. The strategy is set. The real question is, which of these cognitive tools will you remember to reach for when the exam paper tries to pull a fast one on you? Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. I'll see you in the next strategy session.